الرحمن الرحيم والصلاة والسلام على رسول الله صلى الله عليه وسلم. Assalamu alaikum. Mademoiselle Bورجيبة Zeynep, vous avez présenté une thèse intitulée Études théoriques par la DFT des propriétés structurales, électroniques et magnétiques des composés Mg, MyX, TMX, SE, Tm égale Mn et Chrome, et des propriétés thermodynamiques des composés Mg, MyX, Chrome, Sélénium. Les membres de jury ici présents ont évalué votre thèse et ont émis un avis favorable pour la soutenance publique en vue de l'obtention du diplôme de doctorat 3e cycle en physique des matériaux. Les membres de jury ici présents sont les examinateurs Madame Botalfa Beriza, maître de conférence à l'Université de Guelma, professeur Monsieur Baziz de l'Université de Msila. Le travail a été dirigé par le professeur Atman Medoul et moi-même, je suis présidente du jury. Je vous invite pour nous faire une présentation brève de 30 à 45 minutes dans laquelle vous allez exposer l'essentiel de vos travaux de recherche. À l'issue de cette présentation, les membres du jury vont poser des questions, apporter des précisions et faire des remarques. Je vous donne la parole et bon courage.
Thank you so much, Your Honor. Bismillah ar-Rahman ar-Rahim. The President and my pleased jury. Perfect morning for everyone here. Thank you for coming. Today I came after 5 years to defend my thesis, which under the title Études théoriques par la DFT des propriétés structurales, électroniques et magnétiques du composé MgSe dopé en manganèse et chrome et des propriétés thermodynamiques du composé MgSe dopé chrome. Now I present to you the most important points I will address it. First, we have preface, next theory and method of computation, results and discussion, and finally conclusion and perspectives. Our work is mainly based on spintronics field, which use the spin of the electron and its charge to speed which use the spin of electron and its charge to increase the speed of the data processing and reduce energy consumption. For information processing, we use the semiconductor to control the gap and the doping. And for the data storage, we use magnetic materials. In this context, diluted magnetic semiconductor or semi-magnetic semiconductor are promising candidates in spintronics field. They have attracted the scientists in the last few years. The DMS's simple definition is a proportional of a semiconductor replaced by magnetic ions of transition metal or rare earth. For that, we can preservation semiconductor character and have ferromagnetic materials. Our goal is the prediction of new ferromagnetic semiconductor materials for spin electronics applications. In our work, we use zinc blende and rock cell structure, and our compound is MgSe as the host material. For the doping, we use the Tm, which is manganese, and the chromium, which the attractive and conventional way to introduce magnetism in the non-magnetic materials is the substitutional doping of transition metal impurity in the host material. But why we choose the MgSe? Because it is based on 2,6 semiconductors, and the 2,6 semiconductor, the crystallographic compatibility with exciting devices, their carriers have long life, higher efficiency in polarization and spin injection, and they are independent ferromagnetic and semiconductor properties. And as well, MgSe is a very attractive binary semiconductor with both N and P tip doping ability, could be used in higher temperature, higher power blue and ultraviolet wave opticals, in ZNSE-based laser diode and light imitation diodes as Chaldean materials, and we can use it as well in spintronic devices. In the theoretical method and computation, in this work, we use the spin polarization density function theory under the framework of the full potential linear Zugmant plane wave, which implemented in the VN2K software to study the physical properties of the diluted magnetic semiconductors such as structural, electronic, magnetism, optical, etc. Here we have the results and the discussion. For the part 1, we have ab initio theoretical prediction of structural, electronic, and magnetic properties of 3D manganese doped zinc blend MgSe by using the DFT MBG approach. So first we have structural properties by using a supercell of 8 atoms of zinc blend. We choose manganese as substitutional doping in the Mg site to calculate the lattice parameter and the bulk modulus by using WC-GGA approximation. For the electronic properties, we calculate the spin polarized band structure and the total and partial density of state by using the TB-MBG approach to solve the problem of underestimation of the band gap. Next, we have the magnetic properties. We have calculated the magnetic total and partial, and we have calculated as well the exchange constant values N0 alpha and N0 beta. For the structural properties, first we calculate the lattice parameter for each concentration by using Vigar's law as entry parameter. Then we have minimized the total energy to the volume and fitting it with empirical Birchmeier-Naga equation of state to obtain the ground state structural properties. The calculation of these parameters for the binary internally compounds is with comparison to the experimental and other available theoretical results are presented in table number 1, where the lattice constant of the binary MgSe and NnSe are very close to the experimental values and stay in good agreement with theoretical calculation. There is here we present the lattice parameter as function of manganese concentration for MgSe. So there is some decreases in the lattice parameter, in the lattice constant with increasing manganese concentration, because the ionic radius of the manganese is smaller in comparison with Mg atom. Well, the compressibility in this alloy increases when the concentration of manganese increases, where the compute lattice constant are used in the next calculation of electronic and magnetic properties. For the electronic properties, in case of zero concentration, means we have MgSe, we can see clearly that MgSe is the non-magnetic semiconductor. The Fermi level is set to 0 and indicated by the dashed line. And we can see that this compound has a direct band gap semiconductor in the gamma direction. For the dose, the first range from -11 to 10 electron volt is mainly dominated by 4s Se orbitals. For the following range, from -3 to near the Fermi level, we have 4p orbitals of Se, while the last region from 4 electron volt to 12 is dominated by 2p, 3s Mg and 4p Se orbitals respectively. For the electronic properties, both the spin orientation up and down with the concentration equals 0.25, 0.15, we have a ferromagnetic semiconductor. where the maximum of the valence band situated at gamma point of the brilliant zone which process the semiconducting matter in these alloys. Same observation for MgSe doped with manganese in 0.75 concentration. For the MnSe, we have the same observation. We have ferromagnetic semiconductor in the two directions. In this table, we have present the calculated band gap values for each concentration. The band gap, not through the table, but the value of the binary MgSe is equal to 4, which is good agreement with the other theoretical and experimental works, and this is due to the use of the MBG approximation. In the figure, we present the band gap values in the spin up and down direction as function of manganese concentration. In the spin up case, the energy gap value decrease with the increase of concentration in our compound, where in the spin down case, the energy gap keep particularly the same values, which is around 3.8. Here we present the total and partial density of state for each element. So for the first range between minus 12 until 11 is formed by 4s orbitals of Se atoms for both spin up and down orientations. In the middle part range around -5 to near the Fermi level, the density of state came essentially from the hybridization between 3D Eg and 3D Teg manganese and 4p Se and 3s Mg states in the spin up case. Conversely, the spin down case is dominated by 4p and 4s Se states. In the last one, is located between 1.2 and 15 electron volt, which divided in two subbands. The first one states from 1.2 to 5 electron volt formed by 3D Teg manganese states for the spin down case, where the second part, situation between 5 to 15, mainly composed mixture of 4s 4p, Se, and mainly composed with a mixture of 4s, 4p, Se, and 4p and 3s Mg orbitals for both spin up and down orientations. In the case of ferromagnetic MnSe, means that the concentration equal to 1. The dose in the first range between -12 to -15 to 12, mainly dominated by 4s Se orbitals for both spin orientation. The second range from -5 to near the Fermi level, the density of state of spin up case came from the hybridization between 3D Eg and 3D Teg manganese and 4s Se orbitals, where the spin down case is dominated essentially by the 4p Se orbitals. Also, the range between 0.5 electron volt to 5 electron volt is dominated by 3D Eg and 3D Teg manganese states for the spin down case. Here we present the we calculate the total magnetic and partial local magnetic moment for each concentration. The value of the total and local magnetic moment. Through the table, we observe that the local magnetic moment of manganese doped MgSe is reduced less than the predicted Hens values due to the hybridization of PD exchange. On the other hand, a small contribution of local magnetic moment is induced on the non-magnetic Mg and Se sites. The negative sign So in this table, we present the calculate conduction and valence band age spin splitting and the exchange constant. So by using these two equations, we can say that the negative sign of both N0 beta and N0 alpha confirms the double mechanism exchange in our compounds where the SD and PD interaction are parallel and support ferromagnetic character. The part number 2, we have a systematic study of structural, magnetoelectronic, and thermodynamic properties of MgSe doped with chromium in the rock cell structure phase for spintronic application. For structural properties, we have used a supercell of 8 atoms in the rock cell phase. We have used the chrome as substitutional doping in the Mg site. And we calculate the lattice parameter and the bulk modulus by using WCGA approximation. For the electronic properties, we have calculated the spin polarized band structure, partial and total density of state by using TB-MBG approximation. And for the magnetic properties, we have calculated the total magnetic moment, the partial magnetic moment for each concentration. We have calculated as well the exchange constant. And for the thermodynamic properties, the results of the structural properties used to calculate the thermodynamic properties by using the quasi-harmonic Debye model as implemented in the Gibbs program. And we have the parameters that we will discuss it later. For the structural properties, we have minimized the total energy to the volume and fitting it to the empirical Birchmeier-Naga equation of state to obtain the ground state properties, the calculated this is the results actually. And the calculated parameters are displayed in table number 1. The values of the lattice parameter for the binary MgSe is in good agreement with other theoretical works and equal to the experimental values. In addition, the lattice parameter in this allows decrease when the concentration of chromium increase because the atom of chromium is smaller than the Mg. On the other hand, the compressibility in this allows increases when the concentration of chromium decreases. In addition, to justify the existence of our compound MgSe doped with chromium for different concentration in the rock cell ferromagnetic structure, we have computed the defect formation energy, and we have as well calculated the corrosive energy. We have also realized that both formation energy and corrosive energy have negative sign. These results indicate the performance of our compounds in the rock cell structure, which suggests that this system under study can exist in the rock cell phase. For the electronic properties, for these materials, both the band structure and the total density of state of the majority spin up show metallic nature with the presence of a large peak centrated at the Fermi level. On the other hand, the minority spin down gives a direct band gap semiconductor with the top of the valence band and the conduction of the the top of valence band and the bottom of the conduction band located at gamma point of the first Brillouin zone. For the electronic properties as well, in the concentration of 0.75, same observation, we have a half metallic character, and the calculated band gap values are presented in the table 2. The values, we can see that when we increase the concentration, the band gap decrease. Here we have the total and partial density of state for each concentration. So we observe that for all three compounds, the lower part of valence band between -15 to -12 is occupied by 4s Se states for both spin cases, and thus in the middle part of valence band in the energy range between -7 to -3.5 is formed by 4p and 3d chromium state. Furthermore, the values of the density of state at the Fermi level in the spin-up case is equal to 0.61, 1.13, 1.86. We note that the contribution from the 4pSe and the 3dTEG states are smaller. So as results, we have like a half metallic character as shown in the figures for the three concentration, as well in the density of state. In this table, we present the exchange splitting energy. We have calculated the exchange splitting energy, which is defined as the separation between the spin up and down peaks. And we compare it with the ununique crystal field energy. And also we calculate the PD, energy interaction, according to the table number 2. We can see that the values of the DD coupling are much higher than the energy of crystal. These results confirm the presence of the ferromagnetism in these compounds. The negative exchange splitting gap values mean that the effect's potential for the minority spin is more attractive as compared to the majority spin, which characterizes the spin polarized system. For the magnetic properties, from the table, we can see that the local magnetic moment of chromium and purity at different concentrations are smaller than the predicted Hand's rule value of 4 total magnetic moment, which they caused by the hybridization of the PD of D of chromium and P of Se states. In addition, we can see a small magnetic moment localized on the non-magnetic Ng and Se sides. It shows that the values, here we have calculated as well the exchange splitting. It shows that the values of N0 alpha are positive, where N0 beta values are negative for all three compounds, indicating that the valence band of 3D states of chromium and the ferromagnetic between the conduction band and the chromium valence spin respectively. Indicate that antiferromagnetic occurs between the valence band and 3D states of chromium and the ferromagnetism between the conduction band and the chromium spin. So, for the thermodynamic properties, we present the variation of the heat capacity inversion of the temperature at different pressure. It can be seen that from 0 to 300 Kelvin, the capacity, the heat capacity increased exponentially following the T3 law for different concentrations. Here we present the variation of heat capacity CV as function of temperature at different pressure. It can be seen that from 0 to 300 Kelvin, CV increased exponentially following the 3D law and have similar behavior for three compounds. And then when T upper 300 Kelvin, CV tends through a limit value known as the Putty-Donning limit. In this figure, we present the variation of the entropy as temperature in different pressure. We can see that the figures show that when S increased sharp, the figures show that S increases sharply when the temperature increases, and decrease with the increase of the pressure at different temperature. In this figure, we present the relationship between volume and the temperature at different pressure for our DMS compound. The results show that at given pressure, V increases slowly with the temperature, especially at higher pressure. On the other hand, V decreases with the increasing of the pressure at different concentration. On the other side, the thermal exposure coefficient is essential parameter. So in this figure, we depict the effect of the temperature and the pressure of this coefficient, where for a given pressure, we can see that alpha increases quickly with the temperature up to 300 Kelvin, and above this temperature, it tends to nearly constant value. Here we have the evaluation of the bulk modules compound. We evaluate the bulk modules at different pressure in function of temperature. We observe that at given pressure, B decreases with the temperature, and when the values of this parameter increase, B increase. So here we have the conclusion and perspective. Diluted magnetic semiconductors have both semiconductoral and ferromagnetic properties, which proves the possibility to manipulate the electronic charge and spin at the same time. Their main physical properties were obtained by first principle calculation based on spin polarized density function theory under the framework of the full potential linear Zugmund plane wave, which is implemented in VN2K software. The compound which were the subject of this thesis have the general formula MgSe Tm, which Tm is the manganese and chromium with different concentration from 0.25 to 0.75. We calculate their structural, electronic, and magnetic properties. The calculation of thermodynamic properties concerned only the compounds doped with chromium. Our results of structural properties are original. The equilibrium and lattice constant of MgSe doped with manganese decrease with the addition of Mn dopant. For the electronic properties, our compounds maintain a semiconductor nature in the both spin configuration and have a direct band gap. The calculated total magnetic moment for MgSe doped with manganese are about 5, largely from the manganese doping. Also, we can see a small magnetic moment produced on the non-magnetic Mg and Se atoms due to the hybridization between PSE and DMN states. The semiconductor ferromagnetic behavior in polarized spin of the ternary can give them excellent optical and magnetic properties at the same time. From our study, we conclude that when the chromium concentration increases, the lattice parameter decrease. The band structure and the density of states show that the spin polarization in the rock-celled MgSe semiconductor can be introduced via the chromium doping and give half metallic behavior for each concentration, which this investigation predicts that our compounds are good candidates in the future industry spintronic devices such as GMR, TMR, etc. For the three compounds, a large magnetic moment is observed on the magnetic atomic sites, which a small local magnetic moment on the non-magnetic Mg and Se atomic sites caused by the hybridization of PSE and D chromium states. The results proved by the quasi-harmonic Debye model implemented in Gibbs code have shown that the concentration of the dopant chromium and the pressure does not have a significant impact on both Cp, Cv. On the other hand, we observe the effect of Sv and alpha. Finally, in the absence of experimental data, this theoretical study can be considered as good prediction and will be a reference for future work on these materials. As a perspective, this work opens future perspectives as some aspects have not yet been addressed. Therefore, we plan to complete our study on these materials with the following results. Study of optical and elastic properties, study of doped MGSE in the form of thin layer means two-dimensional system. Thank you so much for your kind attention.